Have you ever thought about giving it all up and selling your art on the beach? We're gonna follow the story of Javier, a student that decided to drop out of his program in applied mathematics and selling his art on the beach. In this case, his art are beaded jewelry. And you might be asking, why am I talking about that? And the answer is simple. We're going to be doing a mathematical modeling of that situation and solving it using Julia. So let's start by describing what the situation is for Javier. So Javier has recently decided to drop from his applied math program, and he is selling and building himself beaded jewelry. If you search for bead jewelry on Google, you can see a lot of options, a lot of different kinds of jewelry, and there's also kits if you actually want to start yourself. We're going to be focusing on the mathematical problem though, so that kind of art is what Javier wants to do. His idea is that he's gonna spend his days on the beach. He has a little stand that he can carry around easily, show his goods, and there is some of his time in the day he can build more of that jewelry, either in the beach or at his house. However, since Javier was in the applied mathematics program, he had some optimization class, and he quickly realized that maybe he could use some of those things he learned on this problem. So he has 3 products, necklaces, bracelets, and earrings. And to create these products, he uses 3 materials: beads, string, and wire. And we're gonna simplify and just consider these 3 products to be all the same. And whenever you say a bead, it doesn't matter what kind of bead it is, they are all going to be the same as well. So for each product, we have a different amount of material usage, different selling price, and different time to build them. I have gathered in this table, so you can see, for instance, that a bracelet uses 15 beads, 60 centimeters of string, and 15 centimeters of wire, and can be sold for €25 and takes 2.5 hours to build. So of course these materials have costs. I'm gonna assume linearity here and look at the individual bead. Ignore, for instance, that I have to buy in a pack of 100, and so I'm ignoring, for instance, inventory costs. So the question that Javier wants to answer is, what should I spend my time building? So if I want to work 40 hours, should I build 10 necklaces in those 40 hours? Or should I use 25 hours building 10 bracelets and then 15 hours building 10 earrings? So that's essentially the kind of choice that he can make. Of course, he has a lot of combinations among these to make 40 hours. For this simple problem, there are many ways to solve it. We're going to be taking the optimization route, which is first a route that's going to be more robust in the future when we actually add more issues to this problem. But also because it's my field and the thing I want to talk most. I'm going to add another constraint here. Javier wants to build at least 2 of each product because he wants to show variety. He wants to show the kinds of things that he can do. And another assumption that we're gonna add here is that everything that Javier builds in a week is going to be sold. So during modeling, one thing that I like to do is to describe the sets, the parameters, and the variables, and then I move to the expressions, objectives, etc. Also, depending on the modeling language, it makes more sense to do it this way or another way. For this problem, I'm going to do one that's very simple to understand, although it's not what's more robust for the future. We can talk more about that in future episodes. So the first thing that I'm going to do is say the sets. So I have only 2 things here, the products and the materials. So whenever I talk about the products, I'm going to be using P. P can be used as a subscript, or it can just be used in a sentence. Here, this set of products it can actually be a list of problems, but it can also be the list of indexes for these products. I normally use lowercase single letters for the indexes or the individual elements of a set, and I use this calligraphic uppercase letters for the sets themselves. So these are the parameters that we have. There are many ways of writing these down. Usually I just add bullet points. But since I want to be very descriptive, I actually put it in a table, and I have used a longer description for this identifier. Normally, if you take a mathematical paper, we just use single letters. For instance, the time available could just be T, and selling price could be S. Here I want to be a little bit more verbose in case it's your first time seeing this. So first we have the time availability. I have not talked about this before. The time availability can be, for instance, the 40 hours that he decides to work, but he can work less. We have not defined this yet. There is the product selling price. So for an individual product, what is the selling price? So it's going to be the parameter selling price underscore P. That's for every P in the set of problems. Also notice that all things have unit. That's a great practice. Add the units for your things, not only because they are essential, but also because you can find errors in your code easily. And here, when I have this bracket M, it's because the unit of the material will depend on the material, so I don't know exactly. You also have the material cost. You'll have the hours to assemble a given product. You have the minimal production of the product P, which is this last thing that I showed here. And you have this amount of the material M per unit of product P, which is our only matrix in this thing here. So the first 3 columns of this table is the matrix mat per prod. A little linear algebra addendum here. In some cases you want to be smart with the indexes, because if it's a matrix you can actually do some matrix multiplication. But in many cases for modeling you don't want to care about that at all, because it's going to be transformed internally. After defining the sets and the parameters, we go to the variables. So the variables in this case are only one vector of variables, which are the amount of the product P that I'm going to assemble and sell. Again, as I said, we're going to assume that everything that is assembled is going to be sold. Now that we have the variables and the identifiers, we can jump straight to objective and constraint, which are the 2 things you need for an optimization problem. But it's also very helpful to define expressions. So expressions are essentially an intermediate description of what you're computing. They, in some cases, can be understood as new variables that you're creating with an attached constraint. That is one way of doing it. It's usually not preferred, but depending on your modeling language, if you don't have the support of expressions natively, what you can do instead is do exactly what I said. You create a new variable called revenue, and you add a constraint, which is the revenue is equal to this thing here. Enough about the theoretical of expressions. Let's look at the actual expressions. So the revenue is going to be how much we are making. So for every product that I build, I'm going to have a selling price. I multiply these 2. I have how much I made, and I sum it over all products. So it's essentially how much am I getting when I sell my products. There is the total used materials. So if specific product uses this mat per prod amount of materials, so the amount of products that I make can be multiplied by that, so I can know how much material I'm using. And I sum it over all the products. I'm going to know how much was used for that given material. And from that, I can compute the total cost, which is exactly the same idea as the revenue. I'm just summing how much material I use times how much they cost and overall materials. Summing overall materials. Another expression, the time spent is again going to be very straightforward. The assemble time of a product times the number of products. And I sum it over all products. That's it. Now, finally, the objective and the constraints that get much more easy to describe when you create intermediate expressions. So I want to maximize the profit. That means I want to maximize the amount revenue minus the cost, which is the definition of profit. And you have the following constraints. The spend time must be limited by the available time, and the production must be larger than the minimum amount of production. We're going to go over the optimized production function now. If you don't want to look into the code and you want to skip ahead to just say the results, you can do that. But that's probably the most interesting part for many of our users. So we're going to dive into that. So we are using jump for this optimization. You will normally write using jump. But since we are using Pluto, this using jump is in a whole different cell. And also we are using the CBC optimizer, which is a simple optimizer that handles integer variables. So this is necessary if you want to copy this to your script. So we're going to create a function, optimize production. It is a function of the available time. And this is the jump syntax. You say I have a model. It's going to be solved by a CBC optimizer. I don't want to display a lot of things here because it's Pluto and just want to show the thing. Because of the choices that I made, I'm going to create an indexing. As I said before, you can create the products and the materials as indexes. But in this case, I created them to be the actual list of materials. So if you look into products, you actually have a list of products, right? So this is an option. You can do that. In Jump will accept these things as arguments. So this product index is essentially inverting the enumerate function. So the enumerate of the products is just this. Maybe there's an easier way of doing it, but it's a small problem, doesn't make any difference. So first we create a new variable for the model. The variable is being called prod. I'm using the same identifiers as I used in the table, so if you want, you can just check it out. So the prod is indexed over the products, right? So subscript P. P equals products means that I am indexing for this set, and that the index that I'm going to be using here locally is P. And each product must be greater than or equal to the min prod, which was one of our constraints. And the index of min prod is products index P. Whenever you see products index P, that's the indexing magic of product index, okay? So our first expression, we have the total used materials. It is an expression that depends on the material. So the same idea here. For each M in materials, I'm defining an expression. And the expression is to sum over material per product of PM, right? So remember, index of the product P, index of the product M, times the prod P. So as you see, it is a little bit on the verbal side. The first alternative, as I already said, is to change product to be an index 1, 2, 3. In particular here, I could also have used enumerator again, but if I build product index, I might as well use it. I have another expression here, and I don't have to declare it as an expression. The total used materials times the material cost. So the dot product here is the element-wise multiplication. So this is total used material subscript M times material cost subscript M. And I'm summing over that. So this is this expression right here. Right? Total used material M times material cost M. When I use the dot product, I create a new vector and I just sum it over with the sum. So I have another linear algebra information here. You can do this with a dot product instead. So I could just change this to dot and do this way. This is the same computation. And I could do this with the mathematical syntax for a dot product, which is to use the quote symbol. So this is like vector transpose times vector. I don't like this way because now it becomes too syntaxy. This is a little bit more clear using the dot. So, but if you want to follow the expression a bit more closer to what the mathematical definition was, this one is good enough. But if you want to be very, very clear on what's being summed over, you can, of course, write this way for M in materials. In this case, however, since the total used material is a vector and the material is a string element, you want to use the materials index of M or just for M in enumerate materials. So the actual materials are being ignored, but the index of the materials are being used. That's another alternative. Of course, this is simpler and is expressive enough for this small problem. In the future, we're going to be using index directly, so don't worry about it too much. The other expression is revenue. So revenue is the same idea. Each product times its selling price and sum over all of them. The profit is the revenue minus the cost. And the time expenditure is the hours to assemble times each product summed over. All of these things are expressions. Jump will understand that you're actually doing expression creation because material cost is a parameter and total use material is an expression, so it can multiply this jump expression times a number, and it understands it really well. This is a variable times a number, so it becomes an expression. Jump understands it really well. It's smart like that. Now we can finally define the objective and the constraint. So at objective, the model, maximize profit, and at constraint, the model, limit the time expenditure by the time availability. That's it. The other constraint, remember it was up here. There is another constraint which I have not mentioned, but I could have made it explicit in my description here. So this is the other condition. The production must be integer. We don't want to allow half a necklace to be built, although you could think that it's going to be half built in a week and finished built in another, but we are not doing inventories. We are selling everything the same week, so let's not think about that. So after the model is built, we can just call optimize, and we are returning the product values. So prod is a jump variable. When it finishes optimizing, we can call the value of this product for each one of the products. So this will give back an array of the actual values of the production. Now we're going to jump back into looking at the model solution. So I'm going to close this. So this is the actual explanation of the solution. It's just another table and a simple plot. So the time availability of Javier, it must be at least 16 hours, otherwise he cannot build these 2 of each products that he wanted to do. And you can see here, if I change this time availability, I can see how much of the products is actually being built. So if Javier works 40 hours, the suggested solution will be to build 11 bracelets, 2 necklaces, and 3 earrings. So it's essentially saying that the bracelet has the best profit margin and that you should invest most of your time on that. And you can see here a distribution of unallocated time over the time availability. If he works, for instance, 17 hours, which is this bar here, 1 hour of those 17 is actually useless, and you can also see the result here. From 16 to 17, that extra hour is not being used to produce anything. It's another hour he can take it easy. This is the profit over the amount of hours of work. Of course, if he's working and selling all that he's building, the profit goes up when you build more things. So that's kind of obvious plot to show, but why not? So this is a very simple problem, and here this is again going a bit more into the depths. This is the actual problem being described by inside Jump. As you can see, it is very simple. So the individual things here are like the cost of the bracelet. So the profit of the bracelet individually gets computed automatically. So how do we get to this? So remember that the profit is the revenue minus the material cost, but the material cost is this expression, and the total use materials uses the math per prod times the prod. So Jump internally will take this product that appeared in the revenue up here. So this prod here and this prod here, they will get aggregated or factored in, and you actually just see the result. So in this case, you can interpret this very easily as the individual profit per bracelet. So the bracelet does not give you the most profit, but because the time to build the bracelet is quite larger than the time to build the necklace, the extra profit of the necklace is not enough So you end up building a lot more bracelets. There are many other things that you can actually do with these kinds of analysis. So also we could start asking questions of like, if I start to build necklaces faster, how fast do I need to build them for them to make sense? This is a kind of sensitivity analysis, which we're not going to be touching for now at least. And for this kind of problem, it is kind of, well, it's not going to be fun enough to have any results. And also very important, for many of these integer problems, you can do a lot of sensitivity analysis because the variables are integers and, well, it gets stranger. So as you can see here, it's not linear. When I say I'm gonna increase in 1 hour my production, the increase has 3 different kinds of, well, maybe 4 different kinds of solutions. So it can be nothing, or it can be a little bit, or it can be a lot more. Doing sensitivity analysis with integer variables is not trivial. So if you want to learn more about what's gonna happen with Javier's endeavor, leave a comment. So there are many complications that we can do for Javier's problem. One thing that you might have seen already is that the solution right now is saying just build 11 bracelets, and the rest of the time you build the 2 of each and 1 extra earring with the free time that you got. But if we build 11 bracelets, are we going to sell them all? Does the demand for the bracelets keep the same when I have a lot of bracelets? Well, that's another question for another video. Please like and subscribe, and also remember to click the bell button to be alerted of future videos. Thanks a lot for watching, and I'll see you next time.